A volcano forms when molten rock from deep within the Earth finds a path to the surface through a break in the planet's crust. Deep beneath the surface of the Earth, intense heat and pressure keeps certain rock in a molten state known as magma. When this magma finds a weak point or crack within the Earth's crust, it can rise upward, eventually breaking through the surface to form a volcano. Once this molten material reaches the surface, it is called lava rather than magma, marking the transition from underground to above-ground molten rock. This basic process has shaped mountains, coastlines, and entire islands across nearly every continent on the planet throughout Earth's long geological history. Considering just how directly volcanoes connect the planet's deep interior toward its visible surface offers a genuine reminder that the ground beneath our feet remains far more dynamic than it often appears in daily life. The Earth's crust is divided into massive moving sections called tectonic plates, and volcanoes frequently form along the boundaries where these plates meet. The Earth's outer crust is broken into several massive sections called tectonic plates, which slowly move relative to one another over long stretches of geological time. Volcanoes frequently form along the boundaries where these plates meet, either colliding, pulling apart, or sliding past one another. Since these boundary regions often create the weaknesses and pressure changes that allow magma to rise toward the surface. This connection between plate boundaries and volcanic activity helps explain why volcanoes are not scattered randomly across the globe, but instead tend to cluster along specific, well-defined geological zones. Considering how directly volcano locations connect toward the deeper structure of the Earth's moving crust, offers a genuine appreciation for just how much volcanic activity reflects the planet's own ongoing internal geological processes. The Pacific Ocean is surrounded by a horseshoe-shaped zone containing the majority of the world's active volcanoes, commonly known as the Ring of Fire. Stretching around the edges of the Pacific Ocean is a horseshoe-shaped zone containing a considerable majority of the world's active volcanoes, along with a significant proportion of the planet's earthquake activity, commonly referred to as the Ring of Fire. This zone traces the boundaries of several tectonic plates surrounding the Pacific, creating the geological conditions favorable for widespread ongoing volcanic activity across countries including Japan, Indonesia, Chile, and the western coast of the United States. Scientists continue closely monitoring this particularly active region, given its considerable population density and history of significant volcanic and seismic events. Considering just how much of the world's volcanic activity concentrates within this single geological zone, offers a genuine appreciation for just how unevenly volcanic risk distributes itself across the surface of our planet. Not every volcano looks like the classic cone-shaped mountain most people typically picture when imagining a volcanic eruption. While the classic cone-shaped stratovolcano represents what many people typically picture when imagining a volcano, these particular structures represent just one of several distinctly different volcanic shapes found throughout the world. Shield volcanoes, for example, form broad, gently sloping mountains built up from repeated, relatively gentle lava flows rather than dramatic explosive eruptions. Other volcanic formations include calderas, which are large depressions formed after a volcano's magma chamber empties and collapses, along with considerably smaller volcanic cones and fissure vents that lack any prominent mountain structure at all. Considering just how much volcanic shape and structure can vary, offers a genuine reminder that the word volcano actually encompasses a considerably wider range of geological formations than the single classic image most people typically associate with the term. Hawaii's volcanoes are famous for producing relatively gentle, flowing lava rather than dramatic, violent explosions, typically associated with more famous historical eruptions. The volcanoes found throughout the Hawaiian Islands are famous for producing relatively gentle, flowing lava eruptions, rather than the dramatic, violent explosions, more commonly associated with certain other famous historical volcanic events. This gentler eruption style occurs because Hawaiian magma tends to be relatively fluid and low in dissolved gas, allowing it to flow smoothly, rather than building up the kind of pressure that leads toward violent explosive eruptions. Elsewhere, this particular eruption style has allowed scientists and even careful tourists to observe active Hawaiian lava flows relatively safely compared to the considerably more dangerous conditions found around many other active volcanoes around the world. Considering how differently various volcanoes can behave despite sharing the same basic underlying geological process, offers a genuine appreciation for just how much individual variation exists, even within this single broad category of natural phenomenon. Volcanic eruptions can be so powerful that they measurably affect global weather patterns for months or even years following a particularly significant event. Sufficiently powerful volcanic eruptions can launch enormous quantities of ash and sulfur compounds high into the atmosphere, where they can spread across vast distances and measurably affect global weather patterns for months or occasionally even years following a particularly significant eruption event. These atmospheric particles can reflect incoming sunlight back into space, creating a temporary global cooling effect that has historically been documented following several of history's largest recorded volcanic eruptions. Scientists studying historical climate records have found direct connections between certain major volcanic eruptions and unusually cold growing seasons occurring in the years immediately following those particular events. Considering just how far-reaching volcanic eruption effects can potentially become, offers a genuine appreciation for just how significantly a single powerful geological event can influence conditions across the entire planet. Some volcanoes remain active for thousands of years, while others erupt only once before falling permanently silent for the remainder of geological time. Volcanic activity patterns vary enormously, with some volcanoes remaining active, erupting periodically across thousands of years of recorded and geological history, while others erupt only a single time before falling permanently silent, representing what geologists refer to as monogenetic volcanic formations. This considerable variation in typical volcanic lifespan reflects differences in the underlying magma supply and geological conditions feeding each particular volcanic system. Understanding whether a particular volcano is likely to remain active long-term or represents a single isolated eruption event helps geologists better assess ongoing risk for nearby communities. Considering how much volcanic activity duration can vary between different individual volcanoes, offers a genuine appreciation for just how much individual geological history shapes each volcano's own particular ongoing behavior. Volcanic soil is often remarkably fertile, which explains why many regions with significant volcanic history also support thriving agricultural communities. Volcanic ash and weathered volcanic rock often break down into remarkably fertile soil, rich in minerals that plants require for healthy growth, which explains why many regions with significant historical volcanic activity also support notably thriving agricultural communities despite the underlying volcanic hazard risk. This fertility has historically drawn farming communities to settle near active or dormant volcanoes throughout human history, despite the very real danger these same volcanic systems can eventually pose. This tension between volcanic soil fertility and volcanic hazard risk represents a genuinely significant ongoing consideration for communities living within volcanic regions around the world. Considering how directly volcanic activity can create both agricultural benefit and genuine ongoing danger offers a genuine reminder that natural phenomena rarely fit into simple, entirely positive, or entirely negative categories. Alone. Volcanoes exist not only on Earth, but have also been discovered and studied on several other planets and moons throughout our solar system. Volcanic activity is not unique to Earth alone, with scientists having discovered clear evidence of past or ongoing volcanic activity on several other planets and moons, scattered throughout our own solar system, including Mars and Jupiter's moon, Io, which remains the most volcanically active body currently known anywhere throughout the solar system. Studying volcanic activity on these other worlds offers scientists valuable comparative insight into how volcanic processes can unfold differently depending on a particular world's own unique composition size and internal heat. Sources. This planetary volcanology research helps place Earth's own volcanic activity within a broader cosmic context, extending well beyond our own single planet alone. Considering that volcanoes exist scattered throughout our solar system, offers a genuine reminder that this powerful geological phenomenon represents a genuinely universal process occurring throughout planetary bodies, more generally, rather than remaining unique to Earth alone. Volcanic eruptions can create entirely new land, including new islands that did not previously exist before a particular eruption event occurred. Sufficiently powerful volcanic eruptions occurring beneath the ocean surface can occasionally create entirely new islands that did not previously exist before that particular eruption event, with the newly emerged volcanic rock gradually building upward until it breaks the ocean surface and becomes a permanent, or sometimes only temporary, new landmass. Several notable examples of this dramatic land creation process have been documented and closely studied by scientists in recent decades, offering valuable, real-time insight into the geological processes that have built entire volcanic island chains throughout Earth's long history. Watching a brand new island emerge from the ocean through this dramatic volcanic process offers one of the most visually striking demonstrations of geological creation happening within a genuinely observable human timescale. Considering that volcanoes can literally create new land where none previously existed, offers a genuine appreciation for just how directly this powerful geological force continues actively shaping our planet's surface even today. The temperature of flowing lava can reach well over 1,000 degrees, making it one of the hottest naturally occurring materials found on the surface of the planet. Flowing lava can reach temperatures well over 1,000 degrees, making it one of the hottest naturally occurring materials found anywhere on the surface of the planet, capable of instantly igniting nearly any flammable material it encounters during an active flow. This extreme heat also gives fresh lava its characteristic glowing orange and red color, which gradually fades to a dull black as the material cools and solidifies into new volcanic rock. Scientists studying active lava flows must use specialized heat-resistant equipment specifically designed to withstand these extraordinary temperatures during close observation and sample collection. Considering just how extraordinarily hot flowing lava genuinely becomes, offers a genuine appreciation for just how much raw thermal energy remains stored within the Earth's molten interior. Volcanic eruptions can be classified according to their explosivity, using a scale that ranges from gentle effusive eruptions to catastrophic explosive events. Volcanologists classify eruptions according to a scale, measuring explosivity ranging from gentle effusive eruptions, producing relatively calm, flowing lava, all the way up toward catastrophic explosive events, capable of ejecting enormous volumes of ash and rock high into the atmosphere within a remarkably short period of time. This classification system helps scientists communicate eruption severity clearly and consistently, while also helping compare historical eruptions against one another using a standardized measurement approach. Understanding where a particular eruption falls along this scale helps emergency planners better anticipate the likely scope and severity of hazards a nearby community might need to prepare for. Considering how systematically volcanologists have developed methods for classifying eruption severity, offers a genuine appreciation for just how much scientific rigor underlies modern volcanic hazard assessment. Some of the largest volcanic eruptions in recorded history released so much ash into the atmosphere that they caused a global year without a proper summer season. Certain historically significant volcanic eruptions released such an enormous quantity of ash and sulfur compounds into the atmosphere that the resulting global cooling effect contributed toward a widely documented year without a proper summer season, affecting agricultural harvests and weather patterns across considerable portions of the Northern Hemisphere. This dramatic historical example offers a genuinely striking illustration of just how significantly a single sufficiently powerful volcanic eruption can influence global climate conditions, even in regions located an enormous distance away from the eruption site itself. Historians studying this particular period have documented widespread agricultural disruption and unusual weather patterns directly traceable back toward this singular volcanic event. Considering just how far-reaching this historical eruption's climate effects ultimately proved to be, offers a genuine reminder of just how significantly volcanic activity can influence conditions across the entire globe, rather than remaining limited only to the immediate surrounding region. Volcanic ash is not actually composed of soft burned material the way ordinary ash from a fire might be, but instead consists of tiny, sharp fragments of rock and glass. Despite its name, volcanic ash is not composed of soft burned material the way ordinary ash from a household fire might be, but instead consists of tiny, sharp fragments of pulverized rock and volcanic glass formed when magma is violently shattered during an explosive eruption. This sharp, glassy composition makes volcanic ash considerably more abrasive and potentially damaging compared to what its familiar name might otherwise suggest, particularly for aircraft engines, electronic equipment, and human respiratory systems exposed to significant ash fall. Understanding this true composition helps explain why volcanic ash clouds pose such a serious hazard for aviation, requiring flights to be rerouted or grounded entirely during significant ash-producing eruptions. Considering how differently volcanic ash actually behaves compared to its deceptively gentle-sounding name, offers a genuine reminder that scientific terminology does not always perfectly capture the true underlying nature of the phenomenon being described. Volcanoes can produce their own lightning during particularly explosive eruptions, creating a dramatic natural phenomenon, sometimes called dirty thunderstorms. Particularly explosive volcanic eruptions can generate their own lightning through a phenomenon scientists sometimes informally call dirty thunderstorms, where the friction and static electricity generated by colliding ash particles within the eruption plume creates the same basic conditions responsible for lightning within ordinary weather-related thunderstorms. This dramatic combination of volcanic eruption and lightning creates one of the most visually striking natural phenomena that can be observed and photographed during a sufficiently powerful eruption event. Scientists continue studying this particular volcanic lightning phenomenon, hoping to better understand the detailed physics involved and potentially use it as an additional tool for monitoring eruption intensity in real time. Considering just how dramatically volcanic eruptions can generate their own lightning offers a genuine appreciation for just how much raw energy and dramatic natural spectacle these eruptions can ultimately produce simultaneously. Certain underwater volcanoes remain completely hidden beneath the ocean surface, with their existence only discovered through specialized ocean floor mapping technology. A considerable number of the world's volcanoes exist entirely underwater, hidden beneath the ocean surface, with many of these particular volcanic formations only being discovered and mapped through specialized sonar and ocean floor mapping technology developed in relatively recent decades. Some estimates suggest the majority of Earth's total volcanic activity actually occurs underwater along the extensive network of mid-ocean ridges where new oceanic crust continuously forms as tectonic plates slowly separate from one another. This underwater volcanic activity remains considerably more difficult to directly observe and study compared to volcanoes located on land, requiring specialized underwater vehicles and equipment for close scientific investigation. Considering just how much volcanic activity remains hidden beneath the ocean's surface offers a genuine appreciation for just how much of our planet's ongoing geological activity continues occurring largely out of sight from ordinary human observation. Some volcanoes produce a distinctive blue-colored flame during certain eruptions caused by burning sulfuric gases rather than the molten rock itself. Certain volcanoes, rich in sulfur compounds, can occasionally produce a strikingly distinctive blue-colored flame during particular eruption phases caused by the ignition of escaping sulfuric gases burning at the surface rather than any inherent color of the molten rock or lava itself. This unusual blue flame phenomenon has been documented and photographed at a small number of specific volcanic locations around the world, drawing considerable scientific and tourist interest, given its genuinely unusual and visually striking appearance. Understanding the underlying chemistry responsible for this distinctive blue coloration offers scientists valuable additional insight into the specific gas composition present within a particular volcanic system. Considering just how visually striking and scientifically distinctive this blue flame phenomenon genuinely proves to be, offers a genuine appreciation for just how much visual variety exists even among the world's most extreme volcanic phenomena. Volcanic eruptions have historically been recorded and interpreted through mythology and folklore across nearly every culture that has lived near an active volcanic region. Nearly every culture that has historically lived near an active volcanic region developed its own mythology and folklore, attempting to explain and make sense of the powerful and often frightening volcanic phenomena occurring within their surrounding environment, often attributing eruptions to the actions of powerful gods or spirits believed to reside within the volcano itself. These rich cultural traditions offer valuable historical insight into how earlier human societies understood and coped with living alongside such a powerful and unpredictable natural force long before modern volcanology provided a prose scientific explanation for these same dramatic phenomena. Studying this folklore alongside modern geological evidence sometimes even helps scientists identify historical eruption events not otherwise well documented through traditional written records alone. Considering how consistently volcanic activity has inspired rich cultural mythology across so many different historical societies, offers a genuine reminder that the fascination explored throughout tonight's journey reflects something genuinely ancient and universal throughout human history. Volcanic gases released during an eruption can include substances that pose serious health risks to nearby communities, even without any direct lava or ash exposure. Beyond the more commonly discussed hazards of lava flows and ashfall, volcanic eruptions also release various gases, including sulfur dioxide and carbon dioxide, that can pose serious health risks to nearby communities, even in situations without any direct exposure to lava or significant ashfall. These volcanic gases can cause respiratory problems, contribute toward acid rain formation, and in sufficiently concentrated situations even displace breathable oxygen, creating genuinely dangerous conditions for both humans and animals. Located within affected areas, volcanologists carefully monitor gas emissions from active volcanic systems as one important indicator, helping assess ongoing eruption risk and potential hazard levels for nearby populations. Considering how seriously volcanic gas emissions must be monitored and managed, offers a genuine reminder that volcanic hazards extend well beyond the more visually dramatic lava and ash hazards that typically receive the most public attention. Volcanoes continue to be studied intensively by scientists using an increasingly sophisticated combination of ground-based monitoring equipment and satellite technology. Volcanologists continue studying active and potentially active volcanoes using an increasingly sophisticated combination of ground-based monitoring equipment, including seismometers and gas sensors, alongside satellite technology capable of detecting subtle ground deformation and thermal changes that often precede a significant eruption event. This comprehensive monitoring approach allows scientists to provide increasingly accurate and timely warnings, helping nearby communities prepare and evacuate when necessary before a major eruption actually occurs. Continued investment in this monitoring infrastructure remains a genuine priority for protecting populations living near active volcanic systems around the world. Considering how much sophisticated monitoring technology continues being directed toward volcanic hazard assessment, offers a genuine appreciation for just how seriously this significant natural hazard continues being studied and prepared for by dedicated scientists worldwide. The largest volcanic structures on Earth are not the tallest visible mountains, but rather enormous shield volcanoes that rise gradually from the ocean floor. The largest volcanic structures found anywhere on Earth are not necessarily the tallest visible mountain peaks, but rather enormous shield volcanoes that rise gradually from the ocean floor, with the majority of their total height hidden beneath the surrounding ocean water rather than visible above the waterline. When measured from their true base on the ocean floor all the way to their summit, these particular volcanic structures can actually exceed the height of the world's tallest above-ground mountain peaks, despite their comparatively modest visible profile above the water. This measurement distinction offers a genuinely fascinating reminder that a mountain's true overall scale can sometimes remain considerably hidden from ordinary surface-level observation alone. Considering just how much of these enormous volcanic structures remains hidden beneath the ocean surface offers a genuine appreciation for just how much of our planet's most impressive geological features remain largely invisible to casual observation. Volcanic eruptions can trigger secondary hazards, including mudflows called lahars, which can travel at surprising speed and cause significant damage far from the original eruption site. Volcanic eruptions can trigger dangerous secondary hazards, including fast-moving mudflows called lahars, formed when volcanic ash and debris mix with water from rainfall, melting snow, or nearby rivers, creating a dense, flowing mixture capable of traveling at surprising speed and causing significant damage to communities located considerable distances away from the original eruption site itself. These lahars represent one of the more historically deadly volcanic hazards, since they can occur with relatively little warning and travel through valleys and waterways extending well beyond the immediate area typically considered at risk from a particular eruption. Volcanologists specifically monitor conditions favorable for lahar formation as an important component of broader volcanic hazard assessment for communities located near rivers draining from active volcanic peaks. Considering how far-reaching and fast-moving these secondary volcanic hazards can genuinely become, offers a genuine reminder that volcanic danger zones often extend considerably beyond the immediate visible vicinity of the volcano itself. Certain volcanic eruptions throughout history have been so significant that they contributed toward measurable shifts in global temperature and even influenced historical, political, and social events. Certain historically significant volcanic eruptions produced climate effects severe enough to contribute toward documented shifts in global temperature, which some historians believe subsequently influenced various historical, political, social events, including agricultural failures and resulting social unrest occurring in the years immediately following, particularly severe eruption events. This kind of historical analysis illustrates just how significantly natural geological events can potentially ripple outward into broader human historical developments, extending well beyond the immediate physical disaster alone. Historians and climate scientists continue collaborating to better understand these potential connections between volcanic activity and broader historical human events. Considering how significantly volcanic eruptions may have influenced broader human history, offers a genuine appreciation for just how deeply interconnected natural geological events and human historical development can potentially become. Volcanoes can be dormant for centuries or even thousands of years before suddenly becoming active again, catching nearby communities by surprise. Certain volcanoes can remain dormant, showing no significant activity for centuries or even many thousands of years before suddenly becoming active again, sometimes catching nearby communities by surprise, if historical memory of the volcano's true active potential had faded during that extended quiet period. This particular pattern illustrates why volcanologists emphasize that a volcano's current quiet appearance does not necessarily guarantee it has become permanently extinct, requiring ongoing careful monitoring, even for volcanoes that have remained inactive for a considerable historical stretch of time. Understanding this distinction between dormant and truly extinct volcanic systems remains an important consideration for accurately assessing long-term volcanic hazard risk in a given region. Considering how unpredictably a seemingly quiet volcano can potentially reawaken after an extended dormant period, offers a genuine reminder that volcanic risk assessment requires considerable ongoing vigilance rather than simply assuming. Apparent current inactivity guarantees permanent future safety. Volcanic islands have historically formed some of the most biologically unique ecosystems on Earth, given their isolated origin far from any mainland source of plant and animal species. Volcanic islands, rising up entirely fresh from the ocean floor, begin as completely lifeless rock, which gradually becomes colonized by plant and animal species, arriving through wind, ocean currents, or occasional animal transport, creating some of the most biologically unique and isolated ecosystems found anywhere on Earth. Species arriving on these isolated volcanic islands often evolve along distinctly different paths compared to their mainland relatives, given the isolated conditions and lack of typical mainland competition or predation pressure. This process has produced some of the world's most scientifically significant examples of evolutionary adaptation and speciation, studied extensively by biologists interested in understanding evolutionary processes. Considering how directly volcanic island formation connects towards some of biology's most significant evolutionary case studies, offers a genuine appreciation for just how deeply interconnected geological and biological processes can ultimately become. Volcanic eruptions can produce natural glass formations when lava cools rapidly enough to prevent the formation of typical crystalline mineral structures. When lava cools sufficiently rapidly, it can solidify into natural volcanic glass, rather than forming the more typical crystalline mineral structures found in slower cooling volcanic rock, since rapid cooling does not allow sufficient time for atoms within the molten material to properly arrange themselves into an organized crystal structure. This natural volcanic glass has been used by human societies throughout history for creating sharp cutting tools and weapons, given its ability to fracture into extremely sharp edges when properly worked. Modern scientists continue studying natural volcanic glass formations for valuable insight into the specific cooling conditions and chemical composition present during the eruption that originally produced them. Considering how directly volcanic glass formation connects toward both ancient human toolmaking and modern scientific research, offers a genuine appreciation for just how much practical and scientific value this particular volcanic material has provided across such a considerable span of human history. Certain volcanic regions produce natural hot springs and geothermal features that have been used by humans for bathing and relaxation for thousands of years. Many volcanic regions around the world produce natural hot springs and other geothermal features created when groundwater comes into contact with heat sources deep within active or recently active volcanic systems, producing naturally heated water that has been used by human societies for bathing, relaxation, and in some traditions, believed medicinal purposes for many thousands of years throughout recorded history. These geothermal features continue attracting considerable tourist interest today, while also serving as valuable renewable energy sources in certain regions where geothermal power plants harness this natural underground heat for electricity generation. This dual use, as both traditional relaxation destination and modern renewable energy source, illustrates the considerable ongoing practical value. Volcanic geothermal activity continues, providing human communities. Considering how long humans have appreciated and utilized volcanic geothermal features, offers a genuine reminder that our relationship with volcanic activity extends well beyond simply hazard management into genuine practical benefit as well. Volcanic eruptions can be preceded by warning signs, including small earthquakes, ground swelling, and changes in gas emissions that scientists carefully monitor for early detection. Volcanologists carefully monitor several specific warning signs that often precede a significant volcanic eruption, including increased small earthquake activity around the volcano, gradual ground swelling as magma accumulates beneath the reshape surface, and measurable changes in the volume or composition of gases being emitted from the volcanic system. Recognizing and properly interpreting these warning signs allows scientists to issue increasingly accurate and timely eruption warnings, giving nearby communities valuable additional time to prepare or evacuate before a major eruption actually occurs. This monitoring capability has improved considerably over recent decades, helping prevent what might otherwise have been considerably more severe casualties during several notable eruption events. Considering how much these early warning capabilities have improved volcanic hazard preparedness offers a genuine appreciation for just how valuable dedicated ongoing scientific monitoring continues proving for protecting communities living near active volcanic systems. Volcanic ash can remain suspended in the atmosphere for extended periods, creating spectacular sunsets visible from locations far from the original eruption site. Fine volcanic ash particles launched high into the atmosphere during significant eruptions can remain suspended for extended periods, gradually spreading across enormous distances and creating spectacular, vividly colored sunsets visible from locations far removed from the original eruption site itself. This atmospheric effect occurs because the suspended particles scatter sunlight in ways that enhance certain colors, particularly deep reds and oranges during sunrise and sunset periods, when sunlight travels through a greater thickness of the atmosphere. Historical records document unusually vivid sunsets, observed across considerable distances following several major historical volcanic eruptions, offering indirect evidence supporting written accounts of these significant historical events. Considering how far-reaching this particular atmospheric beauty effect can become, offers a genuine reminder that even the more visually striking volcanic aftereffects can travel remarkably far from their original destructive source. Certain volcanic craters have filled with water over time, forming crater lakes that can display strikingly vivid and unusual coloration. Volcanic craters can gradually fill with rainwater or groundwater over time, forming crater lakes that sometimes display strikingly vivid and unusual coloration, ranging from vivid turquoise to deep green or even reddish hues, depending on the specific mineral content and chemical composition of the water interacting with the surrounding volcanic rock. These visually striking crater lakes have become popular tourist destinations in several volcanic regions around the world, drawing visitors specifically interested in observing their genuinely unusual natural coloration. Scientists studying these crater lakes gain valuable insight into ongoing volcanic activity, since changes in a crater lake's color or chemistry can sometimes indicate shifts in underlying volcanic conditions worth monitoring closely. Considering just how visually striking these volcanic crater lakes can genuinely become, offers a genuine appreciation for just how much natural beauty can emerge from what began as a site of significant volcanic destruction. Volcanic eruptions have occasionally preserved entire ancient communities, remarkably intact, by rapidly burying them under layers of ash, providing invaluable archaeological insight. Certain historically significant volcanic eruptions rapidly buried entire ancient communities under substantial layers of volcanic ash, preserving remarkable archaeological detail regarding daily life within these communities at the moment the eruption occurred, offering invaluable insight for archaeologists studying these particular historical periods. These remarkably preserved archaeological sites have provided historians and archaeologists with an extraordinarily detailed snapshot of ancient daily life, considerably more complete compared to what typically survives through ordinary historical decay and disturbance over many centuries. Excavating and studying these preserved sites continues yielding valuable new historical insight, even many decades after their initial rediscovery. Considering how much valuable historical information volcanic eruptions have inadvertently preserved, offers a genuine reminder that even devastating natural disasters can sometimes leave behind an unexpectedly valuable scientific and historical legacy. Volcanic activity plays an important role in the long-term geological carbon cycle, helping regulate atmospheric carbon dioxide levels across enormously long timescales. Volcanic activity plays an important, though often overlooked role within the long-term geological carbon cycle, since volcanic eruptions release carbon dioxide that had previously been stored deep within the Earth's interior, while various geological weathering processes gradually remove atmospheric carbon dioxide, helping maintain a rough, long-term balance across enormously long geological timescales stretching across millions of years. This natural geological carbon cycle operates on a timescale considerably longer than the more immediate human-caused carbon emissions currently receiving considerable climate change-related attention. Though scientists studying both natural and human-influenced carbon cycles find value in understanding how these different processes interact and compare. Considering how volcanic activity connects toward these much longer natural geological cycles offers a genuine appreciation for just how many different timescales and processes ultimately combine to shape our planet's overall atmospheric composition over time. Volcanic mountains can grow considerably taller over time through repeated eruptions, each adding a fresh layer of material to the existing structure. Volcanic mountains, particularly the classic stratovolcano type, grow taller over time through repeated eruption events, each adding a fresh layer of lava, ash, and other volcanic material to the existing mountain structure, gradually building upward across thousands or even millions of years of ongoing volcanic activity. This layered building process explains why cross-sections of certain volcanic mountains reveal distinct visible layers, each representing a different historical eruption event, allowing geologists to reconstruct a detailed eruption history for that particular volcano. Understanding this layered growth process helps scientists estimate how frequently a particular volcano has historically erupted, informing future hazard assessment for that same volcanic system. Considering how directly a volcano's physical structure records its own eruption history offers a genuine appreciation for just how much valuable geological information remains literally built into these towering natural structures. Certain volcanic eruptions produce distinctive rock formations called pillow lava, when molten rock erupts directly underwater and cools rapidly into rounded shapes. When volcanic eruptions occur directly underwater, the surrounding water causes the erupting lava to cool extremely rapidly, forming distinctive rounded bulbous rock formations known as pillow lava, due to their characteristic rounded pillow-like appearance once solidified. Geologists studying ancient rock formations use the presence of pillow lava as reliable evidence that a particular ancient volcanic eruption occurred underwater, even when that same rock formation is now found on dry land due to subsequent geological uplift occurring over millions of years. This particular rock formation offers geologists a valuable diagnostic tool for reconstructing ancient environmental conditions present at the time a particular volcanic rock formation actually originated. Considering how much historical environmental information can be deduced from a rock formation's particular shape offers a genuine appreciation for just how much detailed geological history remains encoded within the physical characteristics of volcanic rock. Volcanic eruptions have inspired significant advances in disaster preparedness and emergency management practices that have since been applied toward other natural hazard categories as well. Lessons learned from significant historical volcanic eruptions have inspired considerable advances in disaster preparedness and emergency management practices, including evacuation planning, public communication strategies, and hazard mapping. Techniques that have since been successfully applied toward managing other natural hazard categories, including hurricanes and floods, extending well beyond volcanic hazard management alone. This cross-application of emergency management lessons illustrates how progress made addressing one particular natural hazard category can meaningfully benefit broader disaster preparedness efforts more generally. Emergency management professionals continue studying historical volcanic disaster responses, hoping to extract additional, valuable lessons applicable toward improving preparedness for various other natural hazard categories as well. Considering how broadly volcanic disaster management lessons have influenced other emergency preparedness fields offers a genuine appreciation for just how valuable dedicated study of any particular natural hazard can ultimately prove for broader disaster preparedness efforts more generally. Volcanic rock has been used throughout human history for construction purposes, given its considerable durability and widespread availability in volcanically active regions. Volcanic rock, including basalt and pumice, has been used throughout human history for construction purposes, given its considerable natural durability, relatively light weight in certain volcanic rock varieties, and widespread ready availability in many volcanically active regions around the world. Ancient and modern structures alike continue incorporating volcanic rock into their construction, reflecting this material's genuinely practical value, extending well beyond simply representing a hazard to be avoided or managed. Some volcanic rock varieties, including pumice, remain popular today for various practical applications, including certain cosmetic and cleaning products, given their unique lightweight porous structure. Considering how practically useful volcanic rock has proven throughout human history, offers a genuine reminder that volcanic activity has provided humanity with valuable practical building material alongside its more commonly discussed hazard considerations. Volcanic eruptions can produce distinctive natural glass strands called volcanic hair, formed when small droplets of lava are stretched into extremely fine, thin fibers. Certain volcanic eruptions, particularly the gentler flowing eruptions found in Hawaii, can produce delicate natural glass strands, informally called volcanic hair or Pele's hair, after the traditional Hawaiian volcano deity formed. Some volcanoes produce a distinctive blue-colored flame at night, caused by burning sulfuric gases rather than the lava itself glowing blue. Certain volcanoes, particularly those releasing significant sulfuric gas, can produce a genuinely striking blue-colored flame visible at night as these sulfuric gases ignite upon contact with the surrounding air, creating a phenomenon quite different from the more commonly expected orange or red glow typically associated with molten lava. This particular blue fire phenomenon has become a notable tourist attraction at certain volcanic locations known for this specific gas composition, though observing it safely requires careful protective equipment given the genuinely toxic nature of the sulfuric gases involved. Scientists studying this phenomenon gain valuable insight into the particular gas chemistry present at these specific volcanic sites. Considering how strikingly different this blue volcanic fire appears compared to typical glowing lava, offers a genuine reminder that volcanic phenomena can take genuinely unexpected and visually stunning forms. Volcanoes can produce their own localized weather patterns, including volcanic thunderstorms that form directly above an actively erupting volcanic vent. Sufficiently powerful volcanic eruptions can generate enough rising heat and moisture to create localized volcanic thunderstorms forming directly above the eruption itself, complete with their own lightning, rainfall, and sometimes even localized wind patterns distinct from the broader regional weather conditions. This phenomenon illustrates just how significantly a powerful eruption can influence not just the ground and atmosphere immediately surrounding it, but even generate genuinely new, localized weather systems of its own. Meteorologists, studying these volcanic thunderstorms, continue learning valuable lessons applicable toward understanding atmospheric physics more broadly. Considering that volcanoes can essentially generate their own localized weather, offers a genuine appreciation for just how much atmospheric influence a sufficiently powerful eruption can ultimately produce. Volcanic gases released during eruptions can include a range of different compounds beyond simply the commonly discussed ash, including sulfur dioxide, carbon dioxide, and water vapor. Volcanic eruptions release a considerable mixture of different gases beyond simply the more commonly discussed ash, including significant quantities of sulfur dioxide, carbon dioxide, and water vapor, each of which can have different environmental and health-related effects, depending on their particular concentration and how widely they disperse following an eruption. Sulfur dioxide in particular can combine with atmospheric moisture to create acid rain, affecting regions considerably beyond the immediate volcanic eruption site itself. Scientists carefully monitor volcanic gas emissions, both as an important tool for predicting potential future eruptions and for understanding broader environmental impacts these emissions might create. Considering just how varied volcanic gas emissions genuinely are, offers a genuine appreciation for just how much complex chemistry accompanies even a single volcanic eruption event. Volcanoes have been worshipped, feared, and studied by human cultures throughout recorded history, often featuring prominently within religious and mythological traditions. Volcanoes have held tremendous cultural significance throughout human history, often featuring prominently within religious and mythological traditions across numerous different cultures, particularly those living in close proximity to active volcanic regions, where these powerful natural forces became deeply woven into local spiritual beliefs and storytelling traditions. This considerable cultural significance reflects the genuine awe and fear these powerful natural phenomena have consistently inspired throughout considerable stretches of recorded human history. Modern volcanology continues acknowledging and respecting this rich cultural history, even as scientific understanding of volcanic processes has grown considerably more detailed and technically sophisticated over time. Considering how consistently volcanoes have captured human cultural and spiritual imagination throughout history, offers a genuine reminder that the fascination explored throughout tonight's journey reflects something genuinely enduring across considerable stretches of human cultural experience. Volcanic eruptions can be predicted to some degree using modern monitoring technology, though precise timing predictions remain genuinely challenging, even with advanced equipment. Modern volcanologists rely on sophisticated monitoring technology, including seismographs, measuring ground vibration, gas sensors, tracking emission changes, and satellite-based ground deformation monitoring in order to detect warning signs, suggesting a particular volcano may be building toward a future eruption. Despite these considerable technological advances, precisely predicting the exact timing of a future eruption remains genuinely challenging, even with the most advanced currently available monitoring equipment, since volcanic systems involve considerable underlying complexity that continues to challenge even sophisticated predictive models. Continued research and improved monitoring technology continues gradually, improving prediction accuracy. Though perfect, precise timing, prediction likely remains beyond current or even near-future scientific capability. Considering how much monitoring technology exists, yet how challenging precise eruption, timing, prediction genuinely remains, offers a genuine reminder of just how complex volcanic systems ultimately prove to be, even under considerable, dedicated scientific study. Volcanoes exist beyond Earth as well, with several other planets and moons throughout our solar system, displaying their own distinct volcanic activity. Volcanic activity is not unique to Earth alone, since several other planets and moons throughout our solar system display their own distinct forms of volcanic activity, including a moon of Jupiter that ranks as the most volcanically active body currently known anywhere throughout the entire solar system. Studying volcanic activity on these other worlds offers valuable comparative insight, helping scientists better understand the broader range of geological processes capable of occurring throughout different planetary environments beyond Earth alone. This comparative planetary volcanology represents a genuinely fascinating intersection between geology and broader planetary science research. Considering that volcanic activity extends well beyond our own planet, offers a genuine appreciation for just how universal this particular geological process appears to be throughout our broader solar system. Volcanic eruptions can trigger secondary hazards beyond the initial eruption itself, including mud flows called lahars, capable of traveling considerable distances at high speed. Volcanic eruptions can trigger dangerous secondary hazards beyond the initial eruption itself, particularly mud flows called lahars, which form when volcanic ash and debris mix with water, whether from melting snow and ice, heavy rainfall, or a nearby lake, and then travel down volcanic slopes at considerable speed, capable of burying entire communities located along their path. These lahars represent one of the more genuinely dangerous secondary volcanic hazards, precisely because they can travel considerable distances well beyond the immediate eruption site itself, sometimes catching downstream communities by surprise. Volcanic hazard planning increasingly accounts for this particular secondary risk alongside the more commonly discussed direct eruption hazards. Considering how dangerous these secondary lahar hazards can become, offers a genuine reminder that volcanic danger often extends considerably beyond the immediate area surrounding an actively erupting volcanic vent. Volcanic rock and minerals have proven valuable for various practical human applications, extending well beyond simply representing geological curiosities alone. Volcanic rock and minerals have proven valuable for numerous practical human applications throughout history and continuing today, including construction materials, abrasive products, and certain minerals used within various industrial and even cosmetic applications. This practical utility illustrates how volcanic activity, despite its considerable destructive potential, has also provided humanity with genuinely valuable natural resources across many different practical applications throughout history. Geologists and materials scientists continue finding new practical applications for various volcanic materials as research into their particular properties continues advancing. Considering just how practically useful volcanic materials have proven throughout human history offers a genuine reminder that volcanoes provide genuine ongoing benefit alongside their more commonly discussed hazards. Volcanoes continue to be an active and genuinely important area of ongoing scientific research, given their considerable influence on geology, climate, and human safety around the world. Considering everything explored throughout tonight's journey so far, volcanoes continue representing a genuinely active and important area of ongoing scientific research. Given their considerable influence extending across geology, climate, and human safety, for the many millions of people living in proximity to active or potentially active volcanic regions around the world, this continued, dedicated research reflects just how significantly volcanic activity continues, shaping both our planet's physical landscape and the daily lives of countless communities living within volcanic regions. Considering how much dedicated ongoing research continues focusing on volcanoes, offers a genuine appreciation for just how significant this powerful natural phenomenon continues to be for both scientific understanding and practical human safety planning. Volcanic eruptions can be classified using a scale called the Volcanic Explosivity Index, which helps compare the relative size and violence of different historical eruptions. Volcanologists use a standardized scale called the Volcanic Explosivity Index, which helps compare the relative size, intensity, and violence of different historical eruptions, using a consistent measurement approach that considers factors, including the volume of material ejected and the height reached by the resulting eruption column. This standardized scale allows scientists to meaningfully compare eruptions occurring at completely different volcanoes across vastly different time periods, offering valuable historical and predictive context. Understanding where a particular eruption ranks on this scale helps both scientists and the general public better appreciate the genuine relative scale of any given volcanic event. Considering how valuable this standardized comparison scale continues, proving offers a genuine appreciation for just how much careful scientific measurement underlies modern volcanology. Some volcanic craters contain lakes, some of which can be acidic or extremely hot due to their direct connection with underlying volcanic activity. Certain volcanic craters contain lakes formed when rainwater or groundwater accumulates within the crater depression, sometimes becoming remarkably acidic or unusually hot due to their direct connection with underlying volcanic gases and heat sources continuing to influence the lake water chemistry and temperature. These unusual crater lakes can display strikingly vivid colors, including bright turquoise or green hues, resulting from dissolved minerals and chemical compounds present within the acidic water. Some of these crater lakes have proven genuinely dangerous, occasionally releasing sudden dangerous gas bursts or experiencing dramatic temperature and chemistry changes, reflecting shifts in the underlying volcanic activity. Considering just how strange and visually striking these volcanic crater lakes can become, offers a genuine appreciation for just how much unexpected natural beauty and danger can coexist within a single volcanic feature. Volcanic ash differs significantly from ordinary ash produced by burning wood or paper, since it actually consists of tiny fragments of pulverized rock and glass, rather than organic combustion byproducts. Despite sharing the same common name, volcanic ash differs considerably from the ordinary ash produced by burning wood or paper, since volcanic ash actually consists of tiny sharp fragments of pulverized rock, minerals, and volcanic glass created when magma is violently fragmented during an explosive eruption, rather than representing any kind of organic combustion byproduct. This distinct composition helps explain why volcanic ash can prove particularly damaging to machinery, respiratory systems, and aircraft engines, given its genuinely abrasive glass-like particle structure, rather than behaving like the soft ash most people associate with a simple campfire. Understanding this important compositional difference helps explain why volcanic ash warnings deserve to be taken so seriously compared to more ordinary everyday ash exposure. Considering how differently volcanic ash behaves compared to ordinary combustion ash offers a genuine reminder that shared everyday terminology does not always accurately reflect genuinely different underlying material composition, hazard potential. Volcanoes can remain active for tens of thousands or even millions of years, though individual eruptive episodes typically represent a comparatively brief portion of that much longer overall timeline. While an individual volcanic eruption might last anywhere from a few hours to several years, a volcano's overall active lifespan can stretch across tens of thousands or even millions of years, with individual eruptive episodes representing comparatively brief periods of activity, separated by potentially long stretches of relative quiet dormancy. This extended overall timeline helps explain why a volcano showing no recent eruption activity within recorded human history might still be considered geologically active and capable of erupting again someday, given how brief human recorded history remains compared to typical volcanic lifespans. Considering just how much longer a volcano's overall active lifespan proves to be compared to any single human lifetime, offers a genuine appreciation for just how patient and long-term geological timescales genuinely prove to be, compared to our own considerably briefer human experience of time. Volcanic eruptions have occasionally been documented creating temporary but genuinely spectacular sunset displays as ash particles scatter sunlight in unusual and vivid ways. Following major volcanic eruptions that inject significant ash and aerosol particles into the upper atmosphere, observers around the world have occasionally documented genuinely spectacular and unusually vivid sunset displays as these particles scatter incoming sunlight in distinctive ways not typically seen during ordinary atmospheric conditions. These striking atmospheric displays can persist for months following a sufficiently significant eruption, sometimes appearing in regions located thousands of miles away from the original volcanic eruption site itself. Artists and writers throughout history have occasionally documented and even been directly inspired by these unusual volcanic sunset displays following particularly significant historical eruptions. Considering how far-reaching and visually striking these volcanic sunset effects can become, offers a genuine appreciation for just how broadly a single powerful eruption's influence can extend across the entire globe. Volcanic monitoring stations around the world continuously collect data, helping scientists track subtle changes that might indicate a volcano's changing activity level. A global network of volcanic monitoring stations continuously collects detailed data, including ground deformation measurements, gas emission readings, and seismic activity tracking, helping scientists identify subtle changes that might indicate a particular volcano transitioning toward increased activity levels, potentially signaling a future eruption. This continuous monitoring effort requires considerable ongoing investment and international scientific cooperation, given how many active and potentially hazardous volcanoes exist scattered across the globe. Advances in monitoring technology continue improving the sensitivity and reliability of this important ongoing data collection effort. Considering how much continuous monitoring effort volcanoes require offers a genuine appreciation for just how much dedicated scientific infrastructure continues supporting global volcanic hazard awareness and public safety planning. Volcanic eruptions have historically influenced global food security when sufficiently significant eruptions cause temporary but widespread crop failures related to temporary global cooling effects. Certain historically significant volcanic eruptions have caused measurable, temporary, global cooling effects sufficient to trigger widespread crop failures and resulting food shortages across multiple different regions during the years immediately following a particularly significant eruption. Historians studying these historical events have documented connections between certain major volcanic eruptions and subsequent periods of documented famine and social disruption occurring in regions located considerable distances from the actual eruption site itself. This historical connection illustrates just how significantly a single, sufficiently powerful volcanic eruption can influence global conditions, extending well beyond simply the immediate eruption site and surrounding region alone. Considering how directly historical volcanic eruptions have influenced global food security, offers a genuine reminder that volcanic impacts can ripple through human society in ways extending considerably beyond the more immediately obvious. Direct eruption hazards alone. Volcanic activity can create geothermal energy resources that some countries have successfully harnessed as a genuinely renewable source of electricity and heating. Countries located within particularly active volcanic regions have successfully harnessed the underlying geothermal heat associated with volcanic activity as a genuinely renewable energy source capable of generating electricity, providing heating for homes and other buildings without relying on fossil fuels. This practical energy application represents one of the more genuinely beneficial ways human societies have learned to work alongside volcanic activity, rather than simply treating it purely as a hazard to be managed and avoided. Countries with particularly extensive geothermal resources have developed considerable expertise in this particular renewable energy technology that other volcanically active regions increasingly seek to learn from and adapt for their own energy needs. Considering how beneficially certain countries have learned to harness volcanic geothermal energy offers a genuine appreciation for just how creatively human societies continue finding productive uses for this powerful natural phenomenon. Volcanic eruptions can sometimes provide advance warning through changes in nearby animal behavior, though scientists continue debating exactly how reliable this particular warning signal genuinely proves to be. Some historical and anecdotal accounts describe unusual animal behavior changes preceding significant volcanic eruptions, though scientists continue debating and researching exactly how reliable and scientifically valid this particular potential warning signal genuinely proves to be compared to the more established instrumental monitoring methods already discussed earlier. This ongoing scientific debate reflects the genuine challenge of separating anecdotal historical observation from rigorously tested scientific evidence when studying rare and unpredictable natural events like significant volcanic eruptions. Researchers continue exploring this particular question, hoping to determine whether animal behavior monitoring might eventually offer a genuinely valuable supplementary tool alongside more established instrumental volcanic monitoring approaches. Considering how much scientific debate continues surrounding this particular potential warning signal offers a genuine reminder that not every aspect of volcanic science has yet reached a fully settled scientific consensus. Volcanoes remind us that our planet remains a genuinely dynamic and continuously changing place, shaped by powerful forces operating deep beneath its surface. Considering everything explored throughout tonight's journey so far, volcanoes continue reminding scientists and curious observers alike that our planet remains a genuinely dynamic and continuously changing place, shaped by powerful geological forces operating deep beneath its surface, largely hidden from ordinary everyday human observation and experience. This ongoing dynamic nature helps explain why volcanology continues attracting such considerable, dedicated scientific attention, and why volcanic phenomena continue capturing such widespread, genuine public fascination and interest. Considering how dynamically active our planet genuinely remains, offers a genuine appreciation for just how much powerful ongoing geological activity continues shaping the world around us, even during periods that might otherwise feel geologically calm and unchanging from any single human perspective. Volcanic islands often display a predictable pattern of formation and erosion, where new islands eventually shrink and sink back beneath the ocean surface over sufficiently long timescales. Volcanic islands typically follow a predictable long-term geological pattern, where newly formed islands initially grow through continued volcanic activity before gradually eroding and sinking back toward the ocean surface over the course of many millions of years, as the underlying tectonic plate slowly moves the island away from the volcanic hotspot originally responsible for its formation. This predictable pattern has been studied extensively within certain well-documented volcanic island chains, offering scientists valuable insight into long-term geological processes shaping ocean island formation and eventual disappearance. Understanding this long-term pattern helps geologists better interpret the age and geological history of various volcanic islands found throughout the world's oceans. Considering just how predictably this island formation and erosion pattern tends to unfold, offers a genuine appreciation for just how much long-term geological order underlies what might initially seem like unpredictable volcanic island formation. Volcanic hotspots represent a genuinely different type of volcanic activity compared to the more commonly discussed plate boundary volcanism, since they can occur in the middle of a tectonic plate rather than along its edges. Unlike the plate boundary volcanism already discussed extensively throughout tonight's journey, certain volcanic activity occurs at what scientists call hotspots, representing areas where unusually hot material rises from deep within the Earth's mantle, creating volcanic activity that can occur in the middle of a tectonic plate rather than specifically along its boundary edges. As the overlying tectonic plate slowly moves across a stationary hotspot over millions of years, it can create a distinctive chain of volcanic islands or mountains, with the oldest formations located farthest from the current hotspot. Location. This particular volcanic mechanism helps explain certain volcanic island chains that would otherwise seem geologically puzzling, given their location away from any obvious tectonic plate boundary. Considering how differently hotspot volcanism operates compared to boundary volcanism offers a genuine appreciation for just how many different underlying mechanisms can ultimately produce volcanic activity across our planet. Volcanic eruptions can occasionally produce a phenomenon called a pyroclastic flow, representing one of the most dangerous and fastest-moving volcanic hazards known. Among the most genuinely dangerous volcanic hazards, pyroclastic flows consist of an extremely hot, fast-moving mixture of volcanic gas, ash, and rock fragments, capable of racing down a volcano's slopes at speeds sometimes exceeding highway driving speeds, while maintaining temperatures hot enough to instantly destroy nearly anything in their path. These devastating flows have been responsible for some of history's most significant volcanic-related death tolls, given how little warning time they typically provide, and how difficult they prove to outrun once triggered. Volcanologists consider pyroclastic flow risk among the most critical hazards to assess when evaluating potential danger posed by a particular active volcano. Considering just how fast and destructive pyroclastic flows genuinely prove to be offers a sobering reminder of just how dangerous volcanic eruptions can become for anyone located within their potential path. Volcanic bombs are a genuine geological term referring to large chunks of molten or semi-molten rock ejected during an explosive eruption that cool and solidify while still airborne. During explosive volcanic eruptions, large chunks of molten or semi-molten rock, called volcanic bombs, can be ejected with considerable force, sometimes cooling and partially solidifying into distinctive aerodynamic shapes while still airborne, before eventually landing some distance from the erupting vent. These volcanic bombs can vary considerably in size, with some remaining relatively small, while others can weigh many tons, representing a genuinely serious hazard for anyone located within their potential landing zone during an active program. Eruption. Geologists study the size, distribution, and landing pattern of volcanic bombs following an eruption to help reconstruct detailed information regarding that particular eruption's force and characteristics. Considering just how large and dangerous these ejected volcanic bombs can become, offers a genuine reminder that volcanic eruption hazards extend well beyond simply lava flow and ash alone. Some volcanoes have calderas so large that they can only be fully appreciated from an aerial or satellite view, given how much they can dwarf the more commonly pictured smaller volcanic cone shape. Certain particularly powerful historical volcanic eruptions have produced calderas so genuinely enormous that their full scale can only be properly appreciated from an aerial or satellite viewpoint, since standing at ground level within or near such a caldera often fails to convey just how large the overall collapsed volcanic structure genuinely proves to be. These enormous calderas form when a volcano's magma chamber empties dramatically during a particularly massive eruption, causing the overlying ground to collapse inward, creating a vast depression, sometimes stretching for many miles across. Some of these caldera-forming eruptions rank among the most powerful volcanic events documented throughout Earth's geological history. Considering just how enormous certain volcanic calderas genuinely prove to be, offers a genuine appreciation for just how powerful the largest volcanic eruptions throughout Earth's history have ultimately become. Volcanic activity has been linked to certain mass extinction events throughout Earth's deep geological history, suggesting sufficiently massive eruptions can trigger genuinely global environmental consequences. Some scientists studying Earth's deep geological history have found compelling evidence linking certain periods of unusually intense and sustained volcanic activity toward mass extinction events documented within the fossil record, suggesting that sufficiently massive and prolonged volcanic activity can trigger genuinely global environmental consequences severe enough to threaten the survival of numerous species simultaneously. This research continues informing broader scientific understanding regarding just how significantly volcanic activity can potentially influence global climate and environmental conditions when eruptions reach a sufficiently massive and sustained scale far beyond anything documented within recorded human history. Understanding these ancient connections helps scientists better appreciate the theoretical upper limits of volcanic environmental impact potential. Considering how directly ancient volcanic activity may have contributed toward mass extinction events offers a genuine reminder of just how significantly this powerful geological force can influence life on Earth when operating at its most extreme historical scale. Volcanic eruptions can be preceded by swarms of small earthquakes as magma moves through underground channels, creating detectable ground vibration patterns. As magma moves upward through underground channels toward the surface prior to a potential eruption, this movement often generates detectable swarms of small earthquakes, creating a recognizable seismic pattern that volcanologists carefully monitor as one of the more reliable warning signs, suggesting a particular volcano may be building toward future eruptive activity. These earthquake swarms can occur days, weeks, or sometimes even months before an actual eruption occurs, though the exact timing relationship between earthquake activity and eventual eruption remains genuinely difficult to predict with complete precision. Continuous seismic monitoring around active volcanoes represents one of the most important tools volcanologists rely upon for ongoing hazard assessment. Considering how directly earthquake monitoring connects toward volcanic eruption, prediction offers a genuine appreciation for just how interconnected different geological monitoring techniques ultimately prove to be for comprehensive volcanic hazard assessment. Volcanic ash layers found within sediment cores and glacial ice provide scientists with a valuable historical record, helping date and study ancient volcanic eruptions. Careful analysis of volcanic ash layers preserved within sediment cores and glacial ice cores allows scientists to identify and precisely date ancient volcanic eruptions that occurred long before any written historical record could have documented them, offering a valuable extended historical record, stretching back considerably further than human recorded history alone could ever provide. This kind of geological detective work has helped scientists identify and study numerous significant historical eruptions that would otherwise remain completely unknown given how far back in time they occurred relative to any available written historical documentation. This research continues expanding scientific understanding regarding the full historical frequency and scale of significant volcanic eruptions throughout Earth's more recent geological history. Considering how much valuable historical information can be extracted from careful ash layer analysis offers a genuine appreciation for just how creatively scientists continue uncovering detailed volcanic history, extending well beyond the relatively brief span of written human historical record-keeping. Volcanic tourism has grown considerably in popularity as travelers seek to witness active volcanic activity safely from designated viewing areas and guided tours. Volcanic tourism has grown considerably in popularity in recent decades as travelers increasingly seek opportunities to witness active volcanic activity safely from designated viewing areas, guided tours, and specially equipped observation points established at various volcanic destinations around the world. This growing tourism interest has created meaningful economic benefits for many communities located near popular volcanic attractions, while also requiring careful safety planning and monitoring to ensure visitors can observe these powerful, natural phenomena without facing unnecessary risk. Tour operators and local governments increasingly collaborate with volcanologists to establish appropriate safety protocols and viewing distance guidelines for popular volcanic tourism destinations. Considering how much volcanic tourism continues growing in popularity, offers a genuine appreciation for just how strongly these powerful natural features continue capturing genuine public fascination and travel interest. Volcanoes continue offering scientists valuable insight into the fundamental processes shaping our planet's interior and its ongoing geological evolution across enormous timescales. Considering everything explored throughout tonight's journey so far, volcanoes continue offering scientists genuinely valuable insight into the fundamental processes shaping our planet's interior structure and its ongoing geological evolution across enormous timescales, stretching back billions of years into Earth's deep geological history. This ongoing scientific value helps explain why volcanology continues attracting such considerable, dedicated research investment, and why volcanic phenomena continue capturing such widespread genuine curiosity from scientists and casual observers alike around the world. Considering just how much valuable scientific insight volcanoes continue providing, offers a genuine appreciation for just how significantly this powerful natural phenomenon continues contributing toward humanity's broader understanding of our own dynamic and continuously evolving planet. Volcanic rock varies considerably in composition and appearance, ranging from smooth, glassy obsidian to lightweight, porous pumice capable of floating on water. Volcanic rock can take numerous different forms, depending on how quickly the original molten material cooled and how much gas was trapped within it during that cooling process, including smooth, glassy obsidian formed through extremely rapid cooling and lightweight porous pumice containing so many trapped gas bubbles that it can actually float on water despite being solid rock. This considerable variety in volcanic rock types offers geologists valuable clues regarding the particular eruption conditions and cooling history associated with any given volcanic rock sample. Collectors and researchers alike find considerable fascination in the sheer variety of textures and appearances volcanic rock can display depending on its particular formation history. Considering just how differently volcanic rock can form and appear, offers a genuine appreciation for just how much geological information can be read directly from a single piece of volcanic material. Volcanic eruptions can create dramatic and rapid changes to coastlines, particularly when lava flows directly into the ocean, creating new land through rapid cooling and solidification. When active lava flows reach the ocean, the dramatic interaction between molten rock and seawater creates spectacular clouds of steam, while the lava itself rapidly cools and solidifies upon contact with the water, sometimes creating entirely new coastal land within a matter of hours or days depending on the volume and rate of lava flow involved. This dramatic coastal land creation process offers one of the more visually striking and rapid examples of geological change most people could ever hope to witness directly, since most geological processes typically unfold across timescales far too slow for direct human observation. Scientists studying these lava-ocean interactions gain valuable insight into rapid rock formation processes occurring under these particular dramatic conditions. Considering just how rapidly new coastal land can form through this dramatic process offers a genuine appreciation for just how quickly volcanic activity can sometimes reshape our planet's physical geography. Volcanic eruptions have inspired numerous scientific instruments and monitoring techniques specifically developed to better understand and predict this powerful natural phenomenon. The ongoing scientific effort to better understand and predict volcanic activity has inspired the development of numerous specialized scientific instruments and monitoring techniques, including precision tiltmeters capable of detecting subtle ground deformation and specialized gas analyzers capable of detecting minute changes in volcanic emission chemistry that might otherwise go completely unnoticed without this specialized detection equipment. This continued instrument development reflects the genuinely significant ongoing investment scientific communities around the world continue making toward improving volcanic hazard understanding and prediction capability. Engineers and geologists increasingly collaborate closely to develop increasingly sophisticated monitoring technology specifically suited toward the unique challenges volcanic environments present. Considering how much specialized scientific instrumentation continues being developed specifically for volcanic monitoring, offers a genuine appreciation for just how much dedicated engineering innovation continues supporting this important area of ongoing geological science. Volcanic eruptions can occasionally be observed from space, with satellite imagery capturing dramatic ash plumes and thermal signatures invisible to observers on the ground. Modern satellite technology allows scientists to observe volcanic eruptions from space, capturing dramatic images of ash plumes spreading across enormous geographic areas, along with thermal imaging capable of detecting heat signatures from volcanic activity that might not be immediately visible to observers located on the ground, particularly for remote volcanoes lacking nearby ground-based monitoring infrastructure. This satellite-based monitoring capability has proven especially valuable for tracking volcanic activity in remote or difficult-to-access regions where establishing comprehensive ground-based monitoring networks would otherwise prove considerably more challenging and expensive. Continued advances in satellite technology continue improving the resolution and reliability of this valuable space-based volcanic monitoring capability. Considering how valuable satellite technology has become for volcanic monitoring, offers a genuine appreciation for just how significantly space-based observation continues, expanding scientific capability for studying even the most remote and difficult-to-access volcanic regions. Volcanic hazards planning increasingly incorporates detailed evacuation route mapping, specifically designed to help communities near active volcanoes respond quickly and safely during an actual eruption emergency. Communities located near active or potentially hazardous volcanoes increasingly benefit from detailed evacuation route mapping and emergency planning, specifically designed to help residents respond quickly and safely should an actual eruption emergency occur. requiring rapid evacuation from potentially dangerous areas. This kind of detailed emergency planning often involves close collaboration between volcanologists, local government officials, and community members themselves, helping ensure evacuation plans to account for realistic road capacity potential, hazard zones, and the practical needs of the specific population that might require evacuation during a genuine emergency. Regular community evacuation drills help ensure residents remain familiar with established evacuation procedures, even during extended periods when a nearby volcano remains quiet and inactive. Considering how much detailed emergency planning continues developing for volcanic communities offers a genuine appreciation for just how seriously public safety planning continues addressing this significant ongoing natural hazard. Volcanic eruptions can occasionally produce a phenomenon called a volcanic winter, where sufficient ash and aerosol particles temporarily reduce global temperatures for an extended period. Sufficiently massive volcanic eruptions can inject enough ash and sulfate aerosol particles into the upper atmosphere to create what scientists call a volcanic winter, a period of measurably reduced global temperatures, persisting for more years following the eruption as these particles reflect a portion of incoming sunlight back into space before eventually settling out of the atmosphere and allowing temperatures to gradually return toward their normal baseline. Historical volcanic winters have been documented, causing measurable global agricultural disruption and even documented historical famines in certain severely affected regions. This phenomenon illustrates one of the more dramatic ways volcanic activity can influence global climate conditions, even temporarily working in the opposite direction, compared to the warming effects more commonly discussed within broader climate change conversations today. Considering just how significantly a single, sufficiently massive eruption can temporarily cool global climate, offers a genuine appreciation for just how much influence volcanic activity can exert over conditions extending far beyond its own immediate geographic location. Volcanic activity has been connected towards certain unusual atmospheric optical phenomena, including unusually colorful halos, sometimes visible around the sun or moon following significant eruptions. Following certain significant volcanic eruptions, observers have documented unusually vivid and colorful optical phenomena, including distinctive halos visible around the sun or moon, created as sunlight interacts with volcanic particles, suspended within the upper atmosphere in ways that differ from more typical atmospheric conditions. These unusual optical phenomena offer another example of how volcanic eruption effects can become visible to ordinary observers, located considerable distances from the actual eruption site itself, through their influence on atmospheric conditions extending across enormous geographic areas. Atmospheric scientists continue studying these documented historical phenomena, helping build increasingly detailed understanding regarding exactly how volcanic particles interact with sunlight under various different atmospheric conditions. Considering how far-reaching these unusual volcanic atmospheric effects can become, offers a genuine reminder that volcanic influence can manifest in visually striking ways, extending well beyond the immediate eruption region alone. Volcanic eruptions throughout history have occasionally been documented, influencing artistic movements as painters attempted to capture the unusual atmospheric conditions and dramatic skies. These events produced certain historically documented periods of unusually dramatic and colorful sunset conditions following major volcanic eruptions have been connected by art historians towards specific artistic movements and individual notable paintings. Created during these particular historical periods, as artists attempted to capture the genuinely unusual atmospheric conditions and dramatic skies these volcanic events produced. This connection between volcanic activity and artistic expression offers a genuinely fascinating example of how powerful natural phenomena can influence human culture and creative expression in ways extending well beyond the more commonly discussed scientific and practical impacts alone. Art historians and atmospheric scientists have occasionally collaborated to study these documented historical connections in considerable detail. Considering how volcanic eruptions have occasionally influenced historical artistic movements, offers a genuine appreciation for just how broadly this powerful natural phenomenon has touched numerous different aspects of human culture and creative expression throughout history. Volcanic monitoring increasingly relies on community reporting and citizen observation networks, helping supplement more formal scientific monitoring equipment with valuable additional ground-level observation. Many volcanic monitoring programs increasingly incorporate community reporting and citizen observation networks, encouraging local residents living near active volcanoes to report unusual observations, including unusual smells, ground vibrations, or visible changes, helping supplement more formal scientific monitoring equipment with valuable additional ground-level observation that might otherwise go undetected between scheduled scientific monitoring visits. This kind of community involvement helps build stronger connections between scientific monitoring efforts and the local communities most directly affected by potential volcanic hazards, while also providing genuinely valuable additional data points supporting broader monitoring efforts. Volcanologists increasingly value this kind of community partnership as an important complement to more traditional formal scientific monitoring approaches. Considering how valuable community involvement continues, proving for volcanic monitoring offers a genuine appreciation for just how collaborative modern volcanic hazard assessment has increasingly become between professional scientists, the communities they work to protect. Volcanoes ultimately remind us that our planet continues actively building and reshaping itself through processes that have been operating continuously since Earth's earliest geological history. Considering everything explored throughout tonight's especially extended journey through facts about volcanoes, these powerful natural features continue reminding us that our planet remains an actively building and continuously reshaping world through geological processes that have been operating essentially continuously since Earth's own earliest geological history billions of years ago. This ongoing dynamic activity connects the volcanoes we might observe or study today directly back toward the same fundamental processes that helped originally shape our planet's earliest crust and atmosphere. Considering how directly modern volcanic activity connects back toward Earth's earliest geological history offers a genuine appreciation for just how continuously and patiently these powerful geological forces have continued shaping our planet across its entire multi-billion-year history. Volcanic eruptions can differ significantly based on whether the volcano is located on land or beneath the ocean, given how water pressure and access to oxygen influence eruption behavior. Underwater volcanic eruptions behave considerably differently compared to their land-based counterparts, given the significant water pressure present at depth, which tends to suppress the kind of dramatic explosive activity more commonly associated with land-based volcanic eruptions, while the surrounding water also rapidly cools any erupted lava, creating distinctive rounded formations called pillow lava, rather than the more familiar flowing lava patterns typically observed. on land. This considerable difference in eruption behavior helps explain why underwater volcanic activity, despite representing the majority of Earth's total volcanic activity, as discussed earlier, often proceeds with considerably less dramatic visible surface disruption compared to land-based eruptions. Marine geologists continue studying these underwater eruption processes using specialized submersible technology and remote monitoring equipment. Considering how differently underwater volcanic eruptions behave compared to land-based eruptions offers a genuine appreciation for just how significantly environmental context can shape even the same fundamental underlying volcanic process. Volcanic activity has occasionally created temporary but genuinely significant new geothermal features, including geysers and hot springs that attract considerable scientific and tourist interest. Volcanic activity occurring beneath the surface can create geothermal features, including geysers and hot springs, where heated groundwater eventually finds its way back toward the surface, sometimes erupting dramatically at predictable intervals, or simply flowing steadily as a warm or hot spring, depending on the particular underground geological conditions involved. These geothermal features often become significant tourist attractions in their own right, while also offering scientists valuable insight into the underlying volcanic and geological processes occurring beneath a particular region's surface. Some of these geothermal features have remained active and predictable for many generations, while others can change or disappear entirely as underlying geological conditions shift over time. Considering how much scientific and public fascination these geothermal features continue attracting, offers a genuine appreciation for just how many different visible manifestations volcanic activity can ultimately produce beyond simply dramatic eruptions alone. Volcanic eruptions can create dramatic and sometimes life-threatening hazards for aircraft flying through or near volcanic ash clouds, given the genuine risk this ash poses to jet engines. Volcanic ash clouds pose a genuinely serious hazard for aircraft, since the fine glass-like ash particles can be drawn into jet engines, where they melt due to the engine's intense operating heat before resolidifying on interior engine components, potentially causing serious engine damage or even complete engine failure during flight. This serious hazard has prompted the development of specialized international coordination systems specifically designed to track volcanic ash clouds and issue timely warnings, helping airlines avoid affected airspace during significant eruption events. Several documented historical incidents involving aircraft encountering unexpected volcanic ash clouds have helped drive considerable improvement in this particular aviation safety monitoring system over subsequent years. Considering how seriously the aviation industry now treats volcanic ash hazards, offers a genuine appreciation for just how much dedicated safety infrastructure continues protecting air travelers from this particular volcanic hazard. Volcanic eruptions have occasionally been documented, creating temporary but significant changes to local river systems as lava flows or volcanic debris alter existing waterways. Volcanic eruptions can occasionally create significant temporary or sometimes permanent changes to local river systems as lava flows or volcanic debris deposits block existing waterways, forcing rivers to find entirely new paths or creating temporary volcanic dams that can eventually fail catastrophically, releasing sudden dangerous flooding downstream. These hydrological changes represent another example of the cascading secondary effects. A significant volcanic eruption can trigger, extending well beyond the immediate eruption site itself into surrounding watershed systems, Geologists and hydrologists increasingly collaborate to assess these particular secondary flooding risks following significant volcanic events affecting river systems. Considering how directly volcanic eruptions can reshape local river systems offers a genuine reminder that volcanic hazard assessment must account for numerous interconnected secondary effects extending well beyond the initial eruption alone. Volcanic soil composition can vary considerably depending on the particular type of volcanic rock and ash involved, influencing which specific crops grow most successfully in different volcanic regions. The particular composition of volcanic soil can vary considerably depending on the specific type of volcanic rock and ash present in a given region, influencing which particular crops tend to grow most successfully in that specific volcanic soil environment, with certain regions proving particularly well suited toward coffee production, while others favor different crops entirely based on their particular underlying volcanic soil chemistry and mineral composition. This regional variation helps explain why certain internationally renowned agricultural products originate specifically from particular volcanic regions where the local soil chemistry happens to prove especially well suited toward that particular crop's specific growing requirements. Agricultural researchers continue studying these particular soil chemistry relationships, helping farmers in volcanic regions optimize their crop selection and growing practices. Considering how specifically volcanic soil composition can influence successful crop selection offers a genuine appreciation for just how directly geological chemistry can shape agricultural traditions and successful farming practices in volcanic regions around the world. Volcanic eruptions can sometimes be preceded by changes in local groundwater and well water characteristics as underlying geological changes influence water chemistry and temperature. Communities located near active volcanoes have occasionally documented changes in local groundwater and well water characteristics, including unusual temperature shifts or altered mineral content occurring in the period preceding a significant volcanic eruption as underlying geological changes associated with rising magma influence surrounding groundwater systems. While this particular warning signal remains less reliable and less commonly monitored compared to the more established seismic and gas emission monitoring are already discussed extensively throughout tonight's journey, some volcanologists continue studying its potential value as a supplementary warning indicator worth further scientific investigation. Understanding all the various ways volcanic activity can influence surrounding environmental conditions continues expanding the overall toolkit available for comprehensive volcanic hazard monitoring and assessment. Considering this additional potential warning signal offers a genuine reminder that volcanologists continue exploring numerous different possible indicators, hoping to build an increasingly comprehensive and reliable overall volcanic monitoring approach. Volcanic eruptions have historically influenced trade routes and economic development patterns, as certain volcanic materials proved valuable for historical tool-making and construction purposes. Certain volcanic materials, including obsidian, proved genuinely valuable throughout ancient human history for creating exceptionally sharp cutting tools and weapons, leading toward the development of specific historical trade routes, specifically connecting communities toward reliable sources of this particular valuable volcanic material long before modern transportation and trade infrastructure existed. Archaeologists studying these ancient trade patterns continue uncovering valuable insight into how volcanic materials shaped early human economic development and inter-community trade relationships extending back many thousands of years into human history. This historical trade connection illustrates yet another way volcanic activity has influenced human civilization, extending well beyond the more commonly discussed hazard and soil fertility considerations alone. Considering how directly volcanic materials once shaped ancient trade networks offers a genuine appreciation for just how deeply volcanic activity has been woven into human economic history, extending back to some of civilization's earliest developments. Volcanic eruptions can sometimes be observed, producing distinctive sounds beyond simply the commonly expected loud explosive booms, including hissing, roaring, and even occasional musical tones, depending on the particular eruption. Characteristics: volcanic eruptions can produce a surprisingly diverse range of distinctive sounds, beyond simply the commonly expected loud explosive booms, including continuous hissing from escaping gas, deep roaring from sustained lava fountaining, and occasionally even unusual musical or whistling tones created as gas escapes through particular volcanic vent geometries under certain specific conditions. Volcanologists studying these distinctive eruption sounds have found that careful acoustic monitoring can sometimes provide valuable additional insight into a volcano's particular internal conditions and eruption characteristics, beyond what visual observation alone might reveal. This acoustic monitoring represents another example of the creative multidisciplinary approaches modern volcanology continues developing for comprehensive volcanic activity assessment. Considering just how varied volcanic eruption sounds can genuinely become, offers a genuine appreciation for just how many different sensory dimensions a single volcanic eruption event can ultimately produce. Volcanic hazard zones are increasingly mapped using detailed computer modeling, helping predict likely lava flow paths and ash dispersal patterns for various potential future eruption scenarios. Modern volcanologists increasingly rely on detailed computer modeling capable of predicting likely lava flow paths and ash dispersal patterns for various potential future eruption scenarios, helping communities and emergency planners better understand and prepare for the range of different hazards a particular volcano might potentially produce, depending on which specific eruption scenario eventually unfolds. This modeling capability has become an increasingly valuable tool for land use planning and emergency preparedness, helping ensure new development avoids the most hazardous potential zones while also informing detailed evacuation planning. For existing communities located within established hazard zones, continued refinement of these predictive models based on ongoing research and observed historical eruption patterns helps improve their overall reliability and practical planning value. Considering how much computer modeling now supports volcanic hazard planning, offers a genuine appreciation for just how significantly modern technology continues improving practical volcanic safety planning capability. Volcanic eruptions can be classified according to specific named eruption styles based on historically studied volcanoes that displayed particularly characteristic behavior patterns. Volcanologists often classify eruption styles using specific named categories based on historically studied volcanoes that displayed particularly characteristic and well-documented eruption behavior patterns, allowing scientists to quickly communicate general eruption characteristics using this shared standardized terminology rather than needing to describe every relevant detail from scratch each time. These named eruption style categories help create a shared professional vocabulary, allowing volcanologists around the world to communicate efficiently regarding observed or anticipated eruption behavior at various different volcanic sites. Understanding which particular eruption style classification best applies to a given volcano helps inform appropriate hazard planning and public safety recommendations for that specific location. Considering how much shared standardized terminology continues, supporting effective volcanological communication offers a genuine appreciation for just how much careful scientific classification underlies modern volcanic hazard assessment and communication. Volcanic eruptions have occasionally been documented, creating temporary but genuinely significant local cooling effects, even in the immediate vicinity surrounding an active eruption due to ash blocking direct sunlight. Paradoxically, even as an active volcanic eruption releases tremendous heat directly at the eruption site, the surrounding ash cloud can occasionally create temporary but measurable local cooling effects in nearby areas by blocking a significant portion of direct sunlight that would otherwise reach the ground, creating unusually dim and cooler conditions, even relatively close to the actively erupting volcano itself. This localized cooling effect illustrates the genuinely complex and sometimes counterintuitive ways volcanic activity can simultaneously produce both intense, localized heat and measurable nearby cooling, depending on which particular effect a person happens to be experiencing at any given moment and location. Meteorologists studying these localized effects continue gaining valuable insight into the complex atmospheric dynamics surrounding active volcanic eruptions. Considering how counterintuitive this localized cooling effect genuinely proves to be, offers a genuine reminder that volcanic phenomena often defy simple, straightforward expectations once studied in sufficiently careful detail. Volcanic activity monitoring increasingly incorporates drone technology, allowing scientists to safely collect detailed data from hazardous areas that would otherwise prove too dangerous for direct human access. Volcanologists increasingly rely on specialized drone technology to safely collect detailed data, including gas samples, thermal imaging, and high-resolution photography from hazardous areas immediately surrounding an active volcano that would otherwise prove far too dangerous for scientists to access directly without risking serious injury or worse. This drone-based monitoring approach has significantly expanded scientists' ability to closely study active eruption characteristics while keeping human researchers at a considerably safer distance from genuine ongoing volcanic hazards. Continued advances in drone technology and remote sensing capability continue expanding what this valuable monitoring tool can safely and effectively accomplish for volcanic research purposes. Considering how much drone technology has improved, volcanic monitoring safety offers a genuine appreciation for just how creatively modern technology continues, expanding safe scientific access toward genuinely hazardous natural environments. Volcanic eruptions can influence local ecosystems in complex ways, with some plant and animal species surprisingly thriving in the aftermath of an eruption, despite the initial widespread destruction. Following the initial destructive impact of a significant volcanic eruption, surrounding ecosystems often display a remarkable capacity for gradual recovery, with certain pioneer plant species surprisingly thriving in the newly exposed volcanic soil, while various animal species gradually return to recolonize the affected region over subsequent months and years. Ecologists studying this recovery process following significant historical eruptions have documented fascinating ecological succession patterns, offering valuable insight into how natural ecosystems respond to and eventually recover from this particular kind of dramatic environmental disturbance. This recovery process illustrates nature's genuine resilience, even following what initially appears to be complete and total environmental devastation. Considering how remarkably ecosystems can eventually recover following volcanic destruction offers a genuine appreciation for just how resilient natural systems ultimately prove to be when given sufficient time to gradually heal, re-establish themselves. Volcanic eruptions have prompted the development of specific international scientific cooperation agreements, helping share critical monitoring data and expertise across national borders. Given that volcanic hazards do not respect national borders, and given the considerable value of shared scientific expertise, many countries have developed formal international cooperation agreements specifically designed to share critical volcanic monitoring data, research findings, and emergency response expertise across national borders, particularly benefiting nations with fewer domestic scientific resources available for comprehensive independent volcanic monitoring. This international cooperation reflects broader recognition that effectively addressing volcanic hazards represents a genuinely shared global scientific challenge, best addressed through collaborative effort rather than any single nation working entirely in isolation. Continued strengthening of these international scientific partnerships remains an important ongoing priority for improving global volcanic hazard preparedness. Considering how much valuable international cooperation continues developing around volcanic monitoring offers a genuine appreciation for just how significantly this shared global challenge continues, bringing different nations together toward common protective scientific goals. Volcanic ash has occasionally been studied for potential beneficial applications, including certain agricultural and industrial uses beyond its more commonly discussed hazardous characteristics. Beyond its more commonly discussed hazardous characteristics, researchers have occasionally studied potential beneficial applications for volcanic ash, including certain agricultural soil amendment uses and various industrial applications, taking advantage of its particular mineral composition and physical properties. This research reflects a broader pattern already discussed earlier throughout tonight's journey regarding how volcanic materials, despite their considerable destructive potential during an actual eruption, can also provide genuine practical value once properly collected and studied following an eruption event. Materials scientists continue exploring additional potential beneficial applications for volcanic ash and other volcanic byproducts. Considering how researchers continue finding potential beneficial uses, even for volcanic ash, offers a genuine reminder that careful scientific study can often reveal unexpected value, even within materials primarily known for their discrete, hazardous characteristics. Volcanic eruptions can reveal fascinating details about Earth's deep interior, since erupted material sometimes carries fragments of rock from far below the surface that would otherwise remain completely inaccessible for direct study. Certain volcanic eruptions occasionally carry upward fragments of rock originating from remarkably deep within the Earth's mantle, offering geologists a genuinely rare and valuable opportunity to directly study material from depths that would otherwise remain completely inaccessible through any other available scientific method, since drilling to such depths remains far beyond current technological capability. These deep mantle fragments, called xenoliths, provide direct physical evidence, helping scientists better understand the composition and conditions present deep within our planet's interior. Studying these rare volcanic samples has significantly advanced scientific understanding regarding Earth's internal structure and composition. Considering how volcanoes can provide direct physical samples from otherwise completely inaccessible depths offers a genuine appreciation for just how valuable volcanic eruptions prove to be as a unique scientific window into our planet's deep interior. Volcanic eruptions have been studied for their potential role in the very origin of life on Earth, given the unique chemical environments they can create. Some scientists studying the origin of life on Earth have proposed that volcanic environments, including hot springs and underwater volcanic vents, may have provided the unique chemical conditions and energy sources necessary for the world's earliest life forms to eventually develop billions of years ago, long before more complex life existed anywhere on the planet. This research connects volcanic activity toward one of science's most profound and still actively debated questions regarding precisely how life first emerged from non-living chemical processes. Researchers continue studying modern volcanic environments, including deep-sea hydrothermal vents, hoping to gain additional insight into these ancient conditions that may have originally enabled life's earliest development. Considering that volcanoes may have played a role in life's very origin, offers a genuinely profound reminder that this powerful, destructive, natural force may also have contributed toward one of the most significant events in our planet's entire history. Volcanic eruptions continue to be documented and shared through modern digital media, allowing people around the world to witness these dramatic events in near real time, regardless of their own physical location. Modern digital media and widespread internet connectivity now allow people around the world to witness dramatic volcanic eruptions in near real time through live streaming, video, and rapid social media sharing, regardless of their own physical location relative to the actual eruption site, offering unprecedented public access toward directly observing these powerful natural phenomena as they actually unfold. This expanded public access has significantly increased general public engagement with and interest in volcanology, while also occasionally creating new challenges regarding accurate information sharing during active emergency situations. Volcanologists increasingly engage directly with the public through these same digital channels, helping ensure accurate scientific information reaches interested audiences alongside the dramatic visual footage capturing public attention. Considering how directly modern technology now connects the general public toward witnessing active volcanic eruptions, offers a genuine appreciation for just how significantly digital media continues expanding public engagement with this genuinely fascinating natural phenomenon. Volcanic eruptions can vary considerably in duration, with some lasting only hours, while others continue erupting steadily for years or even decades without significant interruption. Volcanic eruption duration can vary enormously, with some relatively minor eruptions lasting only a few hours before subsiding, while certain other volcanoes have been documented erupting steadily and continuously for years or even decades, without significant interruption, offering researchers valuable long-term opportunity to study ongoing eruption processes in considerable sustained detail, rather than the more brief eruption windows typically available for study. These extended long-duration eruptions can create genuinely significant cumulative impacts on surrounding communities and ecosystems, even without ever producing any single particularly dramatic explosive event during their extended active period. Considering just how much eruption duration can vary between different volcanic events, offers a genuine appreciation for just how differently sustained volcanic activity can ultimately unfold compared to the more commonly imagined single, dramatic explosive eruption event. Volcanic research increasingly involves collaboration between geologists and computer scientists, as machine learning techniques are applied toward analyzing the enormous datasets modern monitoring networks continuously generate. Modern volcanic monitoring networks generate enormous quantities of continuous data from seismographs, gas sensors, and satellite imagery, creating genuine practical challenges for human researchers attempting to identify meaningful patterns. Within this vast ongoing data stream, prompting increased collaboration between geologists and computer scientists, applying machine learning techniques specifically designed to help identify subtle patterns that might otherwise go unnoticed. Within these enormous datasets, this interdisciplinary collaboration represents a genuinely promising frontier for improving volcanic monitoring and prediction capability, building upon the extensive existing monitoring infrastructure already discussed throughout tonight's journey. Considering how much modern computing technology continues being applied toward volcanic research, offers a genuine appreciation for just how significantly interdisciplinary collaboration continues advancing this important area of ongoing computing technology. Geological science. Volcanic eruptions ultimately connect toward a genuinely universal human fascination with witnessing raw natural power, given how directly these events display forces far exceeding anything human technology can currently replicate or control. Considering everything explored throughout tonight's especially long journey, through fascinating facts about volcanoes, these dramatic natural events ultimately connect toward a genuinely universal human fascination with witnessing raw natural power, given how directly volcanic eruptions display forces far exceeding anything human technology can currently replicate or meaningfully control. Despite our considerable scientific understanding of the underlying processes involved, this enduring fascination helps explain why volcanoes continue capturing such considerable attention across scientific research, popular media, and everyday human curiosity, regardless of how much scientific understanding continues developing regarding their underlying mechanisms. Considering how universally captivating volcanic power continues, proving to be offers a fitting reminder that some natural phenomena retain their capacity to inspire genuine human awe, regardless of how much scientific understanding humanity continues accumulating regarding their underlying causes. Volcanic hazard education programs increasingly begin at the elementary school level in communities near active volcanoes, helping build lasting familiarity with safety procedures from an early age. Many communities located near active volcanoes have incorporated volcanic hazard education directly into elementary school curricula, helping children develop lasting familiarity with basic safety procedures and evacuation routes from an early age, rather than waiting until adulthood to first learn this potentially life-saving practical knowledge. This early education approach reflects broader recognition that building genuine, long-term community resilience against volcanic hazards benefits considerably from starting this important safety education as early as reasonably possible within a person's life. School administrators in volcanic regions increasingly coordinate closely with local emergency management officials to ensure this educational content remains accurate and appropriately updated. Considering how early volcanic safety education now begins in many affected communities, offers a genuine appreciation for just how proactively communities continue working to build lasting safety awareness across successive generations of residents. As tonight's especially long journey through 100 fascinating facts about volcanoes gradually comes to its own close, it feels worth remembering that somewhere in the world right now, molten rock continues its patient, slow journey upward through the Earth's crust, exactly as it has for billions of years, completely indifferent to human schedules or expectations. Thank you again so much for spending this time with me, exploring the fiery and genuinely powerful world of volcanoes. If you found this video worthwhile, please do consider liking this video and subscribing, since it genuinely helps more curious minds discover this kind of content going forward.